Every time you slide into the driver's seat of an electric vehicle, you put your foot on the brake and you press that glowing start button, you are essentially opening the floodgates to just a massive, potentially lethal reservoir of electrical energy.
Oh, yeah, absolutely.
We're talking about voltages and currents that could, instantly melt metal, cause an explosion, or, deliver a fatal shock. Yet you press the button, the dashboard lights up, a little pleasant chime plays, and you just silently back out of your driveway.
Right.
Why doesn't the car explode? And more importantly, why don't you get electrocuted?
It is, it's the ultimate illusion of simplicity, really. We take it completely for granted because the user experience is just so smooth.
Right, exactly.
But that silent startup, it hides what is arguably one of the most violent, high-stakes choreographies of physics and software happening, anywhere
Yeah.
in modern consumer technology. It is a microscopic war zone in there.
A microscopic war zone. I love that. So today, we are doing a deep dive into the actual battle plan for that war zone. We've managed to get our hands on a highly technical automotive engineering specification document. And it outlines the ASIL D safety standard, which is, it's the absolute highest safety integrity level in the automotive industry. And it specifically targets something that engineers call the high voltage power up and down timing anomaly.
Which, it sounds incredibly dry on the surface, right?
It's totally very dry.
But when you actually read through this documentation, you realize it's a detailed map of how mechanical relays, digital clocks, and heavily fortified software all have to work together in literally a matter of milliseconds.
Wow.
Their entire purpose is just to keep that lethal energy perfectly contained.
So, our mission today for this deep dive is to decode this invisible shield. We're going to break down exactly what happens in the microsecond fractions of time between you pressing start and the car actually being ready to drive. Because engineering at this extreme level, it isn't just about making things work, is it? It seems like it's almost entirely about obsessing over exactly how things break.
Yeah, that is the fundamental philosophy of ASIL D engineering. You start with failure.
Right.
Before you can even design a safety system, you have to map out every single physical, digital, and microscopic ghost that haunts an electrical system. You have to understand the root cause of the fault.
So let's start with the physical world then. The documents describe this incredibly tight window during the power-up phase involving the pre-charge of a DC link capacitor.
Yes.
The car basically has to get this capacitor up to 95% of the battery's total voltage, and it only has a tiny window to do it, somewhere between like 150 to 200 milliseconds. I'm assuming we can't just hook the battery directly up to the motors?
Oh, definitely not, no. Think of the motors as these massive, incredibly thirsty machines, right? And the battery is a giant reservoir.
Okay.
If you just open the floodgates instantly, the electricity rushes in so fast to fill the void that it creates what's called an inrush current. We are talking thousands of amps, just instantly bridging the gap.
Thousands of amps.
Yeah, and that much current would literally vaporize the wiring. So they put a massive holding tank in between the battery and the motor, and that is the DC link capacitor.
Okay, so you have to fill up the holding tank slowly before you open the main valve. That makes sense. But the document points out a major vulnerability here, the physical switches themselves.
Right.
The system uses mechanical relays to connect this power, and relays are, they're basically just giant heavy-duty metal switches controlled by magnets, right?
Exactly. And because they are physical objects with moving metal parts, they're totally subject to the laws of physics and weather. These metal parts, they slide on rails, and those rails are lubricated with grease.
Oh, of course. Grease.
Right, so imagine it's minus 20 degrees outside in the middle of winter. That grease gets thick, it turns into like a cold sludge.
So when the computer sends the signal to close the switch, the electromagnetic coil has to physically fight through that frozen grease to pull the metal contact shut.
Which creates a microscopic delay. The specification actually calls this a pickup delay. The switch takes a tiny fraction of a second longer to close than it normally would in, say, room temperature.
I'm trying to wrap my head around why a fraction of a second even matters. If my car takes an extra tenth of a second to start, I am definitely not going to notice.
No, you wouldn't notice, but the electricity definitely does. In a system operating in milliseconds, a slight delay just completely throws off the entire sequence.
How so?
Well, if the main relay closes before that pre-charge holding tank is at 95% capacity, maybe just because another relay was slow, You get that massive inrush current we just talked about.
Mhm.
And the electricity rushes across the metal contacts of the relay while they are still physically moving. It creates this arc of plasma. It will literally melt the metal contacts together. They just weld shut.
Wow. So the car is just permanently stuck on, or it's completely bricked.
Yeah, or you have a thermal event, which is the polite engineering term for a fire.
That is terrifying. And turning the car off seems just as perilous, honestly. There's a whole section here on the active discharge process.
Yeah.
When I park and hit the power button to turn the car off, the system is legally mandated to bleed all that high voltage out of those holding tanks, getting the entire system below a safe threshold of 60 volts within exactly 2 seconds.
It has to.
Mhm.
Because if you don't drain that capacitor, you have a lethal remnant of energy just sitting there in the vehicle's guts long after the car is completely off.
Right, just waiting.
Imagine a mechanic goes to service the car 5 minutes later, touches a wrench to the wrong bus bar, and just receives a fatal shock.
So to prevent that, the system uses semiconductors, specifically MOSFETs, to route that leftover power into a discharge resistor to just burn it off as heat. But I'm kind of stuck on what happens if a MOSFET breaks. What is a MOSFET actually doing here?
Okay, so think of a MOSFET as a solid-state bouncer at a club.
A bouncer. Okay.
Unlike the mechanical relay, it has no moving parts, no grease. It uses the properties of silicon to either block electricity or let it flow, and it can switch states, millions of times a second.
Wow.
But if that silicon gets electrically compromised, maybe from a random voltage spike, it can shatter internally. If the bouncer passes out, the door is either stuck open or stuck closed.
And if it's stuck closed, that high voltage stays trapped in the holding tank.
Exactly.
So we have physical grease slowing down metal switches and microscopic silicon structures just shattering. But as we move into the digital realm, it seems to get even more chaotic.
Oh, yeah, it does.
The document outlines a digital disconnect, specifically a clock asynchrony. We have the main vehicle controller, the battery manager, and the motor controller. 3 massive computers all needing to coordinate this exact startup sequence.
And to coordinate, they obviously need a sense of time. But they don't just look at one central clock on the wall, They each have their own internal, high-precision hardware clock oscillator right on their circuit board.
So they are literally experiencing time differently. Like, if the battery manager's clock is ticking a microsecond faster than the motor controller, they're drifting.
The technical term is phase sliding.
Phase sliding. Okay, let's unpack this. It's like an orchestra trying to play a symphony in perfect time, but half the musicians are looking at a conductor who is a split second out of sync. The music instantly turns into chaos.
That is a brilliant way to visualize it, actually. And to make matters even worse, the communication network itself, the CNFD network that acts as the car's nervous system, it can get congested.
Like internet traffic.
Exactly. If the network is busy and a critical handshake signal, like the battery saying, hey, I am ready, allow power up, if that's delayed by just 50 milliseconds, the system defaults to panic mode.
Wait, 50 milliseconds? That's like a 20th of a second.
In the realm of ASIL D safety, a delayed message is treated as a compromised message. A late truth is a lie, so it just completely cuts the power.
Wow. But the most mind-bending failure mode in this whole document is how the physical and digital worlds kind of sabotage each other. Have you gotten to the section on ground bounce?
Oh, yes. What's fascinating here is how extreme electromagnetic interference literally forces the physical world to act against the software's intentions.
I read it, but I really need you to unpack the physics for me. The document mentions high DVDT electromagnetic noise. What exactly is DVDT?
So it stands for the change in voltage over the change in time. It is a measure of electrical speed, essentially. Modern EVs use silicon carbide transistors because they are incredibly efficient. But to get that efficiency, they turn on and off at speeds that are honestly hard to comprehend.
Like how fast?
We are talking about a voltage changing at a rate of 10,000 volts per microsecond.
Wait, going from 0 to 10,000 volts in 1/1,000,000th of a second.
Exactly. And when you snap that much energy into existence that quickly, it displaces the electromagnetic field around it. It creates a violent, invisible shockwave of electrical noise.
Okay.
This EMI, electromagnetic interference, is so powerful, it doesn't even need a wire to travel. It just jumps through the air across the physical barriers of the circuit boards.
So where does it go? Does it just hit everything?
It crashes into the low-voltage control lines. Think about the tiny, delicate wire that is carrying a gentle 5-volt whisper from the computer to tell a heavy-duty relay to stay closed.
Right.
This massive 10,000-volt shockwave hits that wire and physically displaces the baseline ground voltage. The ground literally bounces.
So the computer chip on the receiving end gets confused. It's expecting a 5-volt signal, but the baseline just jumped, so it misreads the signal entirely.
Yeah, it thinks the computer just sent a command to turn off.
Mm.
So it drops the relay right in the middle of a high-power operation.
Oh, man.
The physical shockwave from the high-voltage side literally overrode the software on the low-voltage side. And once again, you get massive, unintended arcing and melting metal.
It's like an earthquake shaking the conductor's podium. The software is doing everything right, but the physical environment is hostile. And speaking of hostile environments, we really have to talk about the 12-volt battery.
Oh, the 12-volt. Yeah.
It's wild to me that a cutting-edge EV still relies on the exact same kind of 12-volt lead-acid battery that my granddad had in his truck.
It is kind of funny,
Yeah.
but it is the ultimate Achilles heel of an electric vehicle.
Mm.
You need it because you can't run the radio, the door locks, or, the delicate computer chips off an 800-volt battery.
Mm.
They would instantly vaporize.
Right, you need a stable, low-voltage power supply for all the normal car stuff. But the spec explains that the 12-volt battery is far from stable. When you start the car and all these computers and coolant pumps wake up simultaneously, there is a massive sudden load. The 12-volt battery can sag down to just 6 volts for about 20 milliseconds.
Which is completely terrifying for a computer. Think about how a computer measures anything. To measure the high voltage of the main battery, the computer needs a measuring stick.
Okay.
That measuring stick is a highly precise reference voltage, the VREF, and that is generated by the 12-volt supply.
So if the 12-volt battery sags, the power management chips just start to suffocate. If they can't hold the line, the VREF baseline shakes.
And the math gets completely scrambled. The computer's looking at the high-voltage pre-charge process, and suddenly it thinks the pre-charge failed.
But it didn't actually fail.
No, not because it actually failed, but because its own measuring stick suddenly shrank. The voltage didn't drop, the ruler got shorter. So the system panics and aborts the startup.
Okay, so we have cold grease, exploding silicon misaligned clocks, invisible shockwaves jumping through the air, and shrinking measuring sticks. It is an absolute miracle the car ever turns on.
It really is.
Which brings us to the tech architecture. How do the engineers actually design a digital brain capable of hunting down all these ghosts and stopping them before a fire starts?
Well, the overarching rule of this architecture is speed. The system is designed around the FTTI, which is the fault-tolerant time interval.
Fault-tolerant time interval.
Right. The engineers calculated that if a timing failure occurs, they have exactly 60 milliseconds to catch it and mitigate it. If 61 milliseconds pass, they assume the physical hardware is already melting and a catastrophic event is imminent.
60 milliseconds to diagnose a problem and execute a backup plan. That is, I can't even fathom that. To pull that off, the document outlines a doer-checker state machine. They use a very specific dual-core microprocessor setup.
Yeah, it's a concept called heterogeneous redundancy.
Heterogeneous redundancy.
You don't just have one fast chip doing all the work. You have the main core, the doer. Its entire job is to execute the commands. Close the main relay, start the pre-charge, read the temperature sensors. But sitting right next to it, built into the exact same piece of silicon, is a second core, the checker.
And the checker core doesn't actually drive the car, right? It just watches.
Its only job is to ruthlessly audit everything the doer is doing. It just monitors from the sidelines. During that critical 200 millisecond pre-charge window, the checker is running its own independent math based on the raw sensor data.
Oh, wow.
If the checker sees that the voltage difference between the battery and the holding tank is 20 volts or more, it knows the pre-charge is failing.
So what does it do? Does it politely ask the doer to stop?
It doesn't even talk to the doer. It completely bypasses it. It triggers a hardware interrupt, seizes control of the physical pins on the chip, and forcefully drops the relays to abort the process.
It's like having a pilot flying an airliner, and then a hyper-paranoid co-pilot whose only job is to stare at a completely separate set of dials with their hand hovering over the engine kill switch, just ready to slap it at a millisecond's notice.
That is exactly what it is. And to make sure that co-pilot isn't looking at faulty dials, the architecture mandates redundant senses. They don't just measure the high voltage once. They use two entirely separate hardware pathways to read the same exact voltage.
I actually noticed this in the source, and the contrast between the two methods is fascinating. One pathway is highly digital and modern, an EDSA-DC module.
which stands for Enhanced Delta Sigma Analog to Digital Converter.
Right.
It uses complex, high-frequency digital filtering. It's incredibly fast and accurate, using math to basically filter out the noise.
But the document basically says, complex math can fail in unexpected ways. So the second pathway is entirely different. It's an old-school analog low-pass filter feeding into a basic SAR ADC module.
Right. An analog filter isn't doing math. It is using physical resistors and capacitors like a sponge to literally soak up and smooth out the electrical noise before measuring it. It is brute force, undeniable physical reality.
And the software constantly compares these two wildly different methods, the digital math versus the analog sponge. The spec says if these two readings disagree by more than 5 volts for just 10 milliseconds, the checker core halts everything. It basically says, my eyes are playing tricks on me, I can't trust my own senses, shut it down.
Yeah, it strictly prevents a blind power-up. But my favorite part of the diagnostic software is how it deals with the mechanical ghosts.
Oh, the grease.
Yeah, we talked about the cold, sticky grease causing a pickup delay in the relays. The computer has no cameras inside the relay. It can't see the grease. So how does a digital brain know a physical metal part is struggling?
This part blew my mind when I read it. It uses the magnetic inflection point. It is basically predicting the future using invisible ripples.
It is an incredibly clever application of physics.
Right.
To close a relay, the computer sends electrical current into a coil of wire to create an electromagnet. That magnet pulls the metal switch shut.
Okay.
The software monitors the current flowing into that coil 10,000 times a second.
And as the metal switch finally breaks free of the cold grease and physically snaps shut, it moves through the magnetic field.
And based on Lenz's law of induction, moving metal inside a magnetic field creates a wake. It pushes back.
Yeah.
It causes a tiny, momentary dip in the electrical current flowing into the coil. That dip is the inflection point.
So the software isn't looking for the voltage, it's looking for that specific ripple. It knows that if it sends the command at 0 milliseconds, that ripple should appear at exactly 15 milliseconds.
But if it takes 20 milliseconds to see the ripple, the system knows something is wrong. The relay hasn't failed yet, the car still turns on, but the computer now knows the physical metal is aging, or the grease is freezing, or the coil is overheating.
It's incredible.
It actively logs a diagnostic warning about a timing delay long before a catastrophic failure can occur.
It is doing predictive maintenance on a sealed metal box by reading its magnetic mind. But if we move past prevention, we have to talk about the ultimate nightmare scenario.
Okay.
Let's say prevention fails. You park the car, you hit the power button, but the active discharge resistor, the hardware designed to safely burn off the trapped lethal voltage, is physically broken. The drain pipe is completely blocked.
The FTTI window is ticking. The system has to bleed that voltage below 60 volts in under 2 seconds, but the primary mechanism is dead. This is where the checker core executes what I think is the most brilliant software hack in modern engineering.
Stator copper loss.
Yes, stator copper loss.
Okay, I have to stop you here because when I read this, it sounded insane. The stator is the stationary part of the electric motor. You are telling me that instead of using the motor to spin the wheels, the computer hacks the motor to act as a giant emergency battery drain. Like, if I am parked in my garage, I definitely do not want my car suddenly applying power to the motor and sending me straight through the drywall.
Right, it sounds totally counterintuitive. You are pumping power into a broken system. But it comes down to understanding how a motor actually works. An electric motor is essentially massive coils of thick copper wire.
Sure.
Usually, the computer sends highly orchestrated, alternating electrical pulses into that copper to create a rotating magnetic field, which drags the rotor along and spins the wheels.
Right, and no motor is perfectly efficient.
Exactly. Even the best copper wire has electrical resistance.
Yeah.
Some of the energy you push into it is always lost as heat. Engineers call this copper loss. Usually, you try to minimize it as much as possible.
But in an emergency, the computer weaponizes that inefficiency.
Yes. The checker core completely changes the type of electricity it sends to the motor. Instead of a rotating field, it injects a direct axis current.
Which means what?
It is a specific stationary magnetic pulse that creates absolutely zero rotational torque. The wheels will not move a single millimeter. But it forces massive amounts of electrical energy to shove its way through the resistance of the copper wire.
It turns the motor into a giant harmless space heater.
Exactly. It leverages the massive physical mass and thermal capacity of the motor that is already sitting right there on the axle. It rapidly burns off that trapped lethal voltage, bleeding the entire system below 60 volts in under 2 seconds, completely bypassing the broken drain pipe. It basically turns a liability into a solution.
That is just phenomenal. But brilliant software hacks and dual-core brains need an indestructible physical house to live in. If the physical circuit board melts, the software dies with it. So let's look at the actual drafting table. The design failure mode and effects analysis, or DFMEA. How do they physically bulletproof this blueprint?
Well, let's go back to those mechanical relays. We know they are magnets, but magnets have a nasty habit of fighting back when you turn them off. The document calls it a kickback.
I'm trying to picture this. It's like water hammer in a plumbing system, right? Like when you shut a tap too fast.
Exactly like that. If you have water rushing through a pipe at high speed and you suddenly slam a valve shut, the water has nowhere to go. Its momentum creates a massive pressure spike that bangs violently against the pipes.
Right.
In a circuit, when the computer suddenly cuts the power to the relay's electromagnetic coil, the magnetic field rapidly collapses. That collapsing field generates a violent high-voltage electrical spike that travels backward down the wire, straight toward the delicate silicon microchips that sent the signal.
And a fragile 5-volt microchip cannot handle a 100-volt spike flying at its face. So to stop that, the hardware engineers use TVS diodes.
Transient voltage suppression diodes. They're essentially pressure relief valves installed right in front of the microchip. Under normal conditions, they do absolutely nothing. But the microsecond that high-voltage spike hits them, they break open and violently clamp the voltage down to a safe 40 volts, shunting the excess energy away into the ground plane before it can fry the chip.
It's basically an electrical airbag. But they go much deeper than just adding protective chips, don't they? They actually dictate the microscopic properties of the materials themselves. We talked earlier about the shrinking measuring stick, the 12-volt battery sagging and warping the reference voltage.
Right. To prevent that measuring stick from warping under extreme conditions, the engineers take total control of the bill of materials, the bull of ohm. For those critical voltage sensing circuits, they don't just tell the factory to use, a standard 100 ohm resistor. They mandate the use of class 1 C or G ceramic capacitors and ultra-precise thin film resistors.
The document specifies these components have a 0.1% accuracy. Why do we need military-grade precision for a simple resistor?
Because of a phenomenon called temperature drift. Everything in the physical world expands and contracts with temperature. In standard electronic components, as they get hotter, their electrical resistance changes.
Okay.
But an EV doesn't live in a temperature-controlled server room. It has to start flawlessly after sitting overnight in the freezing tundra at minus 55 degrees Celsius and after baking in a desert parking lot at 125 degrees Celsius.
So if you use a cheap resistor, its resistance changes based on the weather, which means your math changes based on the weather.
Exactly. But these specific Class 1 C0G ceramics and thin film resistors are built from materials that have practically zero temperature drift across that entire extreme range. They don't expand. They don't warp.
That's wild.
By locking down the B-bomb with these specific, slightly more expensive parts, the engineers guarantee that the thermostat never lies. The measuring stick stays exactly the same length, whether you are in Alaska or Death Valley.
Okay, let's unpack this. Here's where it gets really interesting. What about the invisible shock waves, the ground bounce we talked about earlier? If you have a massive 10,000-volt shock wave jumping through the air, you can't just politely ask the noise to leave the delicate 5-volt wires alone. How do you physically build a wall against that?
You build electromagnetic bouncers. The spec mandates heavy-duty common mode chokes on the communication lines.
Unpack a choke for me. How does it physically block the noise without blocking the actual signal you want to send?
So it uses the geometry of the wires. A legitimate communication signal uses 2 wires, and it sends the signal differentially, meaning the voltage goes up on one wire and down on the other.
Okay.
A choke is essentially a magnetic ring wrapped around both wires. Because the legitimate signal is flowing in opposite directions, their magnetic fields cancel out, and the choke lets the signal pass right through like a VIP at a club.
But the shockwave noise?
The shockwave noise hits both wires at the exact same time in the same direction. This is what we call common mode noise. When it tries to push through the choke, the magnetic fields combine and create a massive wall of physical resistance, like over 2,000 ohms of resistance. The choke literally physically chokes the noise out while letting the signal through.
And beyond the electronic bouncers, they enforce a hilariously strict physical rule. The low voltage wires must be kept at least 150 millimeters away from the high voltage lines.
150 millimeters, yes. Space is the ultimate premium inside a densely packed electric vehicle, but this rule is written in blood.
It's like keeping the sensitive communications tent far away from the noisy, heavy artillery on a battlefield.
Perfect analogy. You just cannot route them next to each other, no matter how convenient it would be for the wiring harness. If you violate that physical gap, the noise jumps the gap, corrupts the CAN network, and you get the timing failures.
It is hardware engineering driven purely by paranoia. Look at the active discharge resistor we keep talking about, the drain pipe. The document demands it have thermal armor.
Yeah, thermal armor. When the checker core dumps that lethal energy into the resistor to burn it off as heat, the resistor experiences a violent, instantaneous spike in temperature. It is essentially a controlled explosion of heat.
Wow.
The engineers mandate a thick film resistor that is physically overbuilt to tolerate 3 times the extreme pulse energy that the capacitors can even hold.
And they don't just stick it anywhere on the board. They physically isolate it and paste it directly onto the metal water cooling channels of the power inverter. It is bolted straight to the car's radiator system to ensure that massive spike of heat is instantly pulled away by the coolant.
If we connect this to the bigger picture, it perfectly illustrates how the microscopic decision, like the temperature coefficient of a ceramic capacitor and a macroscopic decision bolting a resistor to a water pipe, are both absolutely required to save a $50,000 vehicle from total failure.
But here is the terrifying reality. You can design the most perfect, mathematically flawless, bulletproof system on a computer screen, and it means absolutely nothing if a tired worker on the factory floor doesn't tighten a bolt enough or uses the wrong solder.
Exactly.
That takes us to the manufacturing side, the process failure mode and effects analysis, or PFMEA. How do they enforce this ASIL D standard when they are building thousands of these a day?
You have to systematically remove human error from the physical assembly. You have to build a factory floor fortress.
The spec outlines the end-of-line, or EOL, interrogation, and they don't just test 1 out of every 100 units. 100% of the power controllers go through this rig. And they don't just test them at a comfortable room temperature, right? They lock them in an oven at 85 degrees Celsius to simulate a hot engine compartment.
Yeah, and it isn't a simple pass or fail test. It is an active calibration. The testing machines automatically inject highly precise laboratory-grade voltages into the circuit board to test those redundant sensors. The machine compares what the sensor reads to what it actually injected. If there is a tiny discrepancy due to, normal manufacturing variations in the silicon, the machine dynamically writes correction coefficients into the chip's memory. It literally calibrates the hardware on the fly.
They also force every single unit to run through the entire mechanical sequence. Pre-charge, close relay, open relay, discharge. If the machine detects that the magnetic inflection point of a relay is even 10% slower than the ideal mathematical curve, a robotic arm automatically diverts that part to a reject track. A human can't even override it.
But the most intense process control is how they handle the high voltage connections. Bolting those massive copper bus bars to the relays is traditionally done by a human with a torque wrench.
But a human with a torque wrench isn't ASIL D compliant, apparently. The document describes smart wrenches, or torque angle fastening, and it starts before the wrench even touches the metal. Optical character recognition cameras, OCR, scan every single bolt to verify it has a specific phosphate coating.
Because the coating guarantees a highly predictable level of friction.
Right. And as the robotic servo-controlled screwdriver tightens the bolt, it doesn't just stop when it hits a certain tightness. It constantly tracks the exact friction curve. It compares the amount of torque being applied against the exact degree of angle the bolt is turning in real time.
If that curve deviates for even a millisecond, maybe there's a microscopic speck of dust in the threads or the bolt is slightly cross-threaded, the machine instantly locks up and halts the assembly line.
It does all of this to guarantee a physical contact resistance of less than 5 microohms. I stopped reading when I saw that number. A microohm is 1/1,000,000th of an ohm. We are talking about a heavy metal bolt holding 2 pieces of thick copper together. Why are we halting a multi-million-dollar assembly line over 5/1,000,000ths of an ohm of resistance?
Because you have to do the math on the absolute worst-case scenario. It comes back to the inrush current we discussed at the very beginning. Remember the thousands of amps of electricity?
Yeah, the massive flood of energy.
There is a fundamental law of physics. Current squared times resistance equals heat loss. I squared R. When your current is 1,000 amps and you square it, you get 1,000,000. You take that massive number and you multiply it by the resistance at that bolt connection.
Oh, I see. Even if the resistance is incredibly tiny, when you multiply it by a million.
Exactly. If a worker poorly tightens a bolt and leaves a resistance of just a few milliohms, the resulting heat generation is astronomical. That tiny gap becomes a highly localized heating element. It will rapidly melt the copper bus bar, destroy the relay housing, and trigger a catastrophic thermal event. 5 microohms matters because it strictly prevents a microscopic flaw from causing a macroscopic fire.
And this obsessive micromanagement extends down to the literal molecular level of the circuit board. They use 3D X-ray machines, automated X-ray inspection, or scanning acoustic microscopy.
Yeah, this is purely to inspect the solder joints, the tiny blobs of melted metal that physically and electrically glue the microchips to the board.
When you melt solder, microscopic air bubbles, called voids, can form inside the liquid metal before it cools. I've soldered wires before, and you never really care about bubbles. But the ASIL D standard is completely ruthless here. Every single circuit board goes through the 3D X-ray.
Because an ED is essentially a giant vibrating box. You're driving over potholes, rumble strips, and dirt roads for 10 years. If you have a hidden air bubble trapped inside a critical solder joint, say, the joint connecting the checker cord to the voltage sensor, that bubble is a massive weak point.
And over years of vibration, that microscopic bubble turns into a microscopic crack.
And one day, you hit a pothole on the highway, the crack spreads across the joint, and it severs the physical connection. Suddenly, your hypoparanoid co-pilot goes totally blind while you were doing 70 miles an hour. The specification states that if the total volume of air bubbles exceeds 5% of the joint, or if a single bubble is larger than 1% in a specific stress zone, the entire board is rejected. The X-rays guarantee the physical foundation of the software is absolutely flawless.
Which perfectly sets up the final gauntlet. The vehicle's brain has been flawlessly designed, it's armored with chokes and diodes, and built with terrifying robotic precision. But before this technology ever reaches a consumer's driveway, they have to prove it actually works. The final phase is Design Verification Plan and Report, DVP&R, Production Validation.
Otherwise known as trial by fire.
Trial by fire.
It is the only way to mathematically prove the ASIL D safety rating isn't just a theoretical fantasy on a drafting table. They take everything they just meticulously built and try to absolutely destroy it in a laboratory.
The testing protocols here are brutal. The shake and bake test sounds like a nightmare for delicate electronics.
The document cites the ISO 27750-3 standard. They take the entire power control module, bolt it to an industrial vibration table, and subject it to violent 3-axis random vibrations. We are talking 35 meters per second squared of acceleration.
That's practically putting the computer inside a commercial paint shaker.
And while it's in the paint shaker, they blast it with thermal shocks in an environmental chamber. They violently swing the ambient temperature from minus 40 degrees to plus 125 degrees Celsius, just back and forth.
And just shaking it and freezing it isn't enough, is it? While it is enduring this physical torture, they force the computer to perform that highly sensitive, milliseconds-long power-up and power-down sequence 1,000 times in a row under maximum electrical load.
And the acceptance criteria to pass this test is staggering. The specification mandates that during all of that extreme abuse, there cannot be a single microsecond of signal loss from any of the sensors. Not one. Furthermore, the physical timing of the mechanical relays cannot drift by more than 5% from their ideal curve.
The system literally has to perform its microscopic ballet perfectly while being violently beaten, and that's just the physical attack. They also try to assassinate it electrically with the brownout test, specifically the LV124 standard.
Yeah, this mimics that 12-volt battery sag we explored earlier, the shrinking measuring stick. But here, they do it maliciously.
Right in the middle of a massive power surge, when the system is under maximum computational stress trying to balance the precharge, the testing equipment intentionally drops the 12-volt supply down to 6 volts for exactly 20 milliseconds.
They are actively trying to induce a failure in the reference voltage. They want to see if the power management chips suffocate, causing the computer to get confused and trigger a false safety shutdown. To pass, the system must recognize the brownout, draw on its specialized Class 1 capacitors to hold the voltage line, and successfully complete the precharge sequence without blinking.
But the absolute climax of this document is the hardware-in-the-loop testing, the HIL assassination.
This is where engineers essentially play the role of digital saboteurs. They hook the computer up to a massive 800-volt simulator. It's kind of like the Matrix. The computer thinks it is plugged into a real car with real motors and real batteries, but it's all a simulation controlled by the engineers.
And then the engineers start feeding the computer lies and broken physics. The spec says they will artificially simulate a melted discharge resistor, or they will inject a line of code that forces a virtual relay to get physically stuck for exactly 35 milliseconds.
They're testing that 60-millisecond FTTI window. The moment the saboteur injects the failure, the countdown begins. The dual-core processor must sift through the redundant sensor data, recognize the injected failure through the noise, and trigger an interrupt within 60 milliseconds.
And recognizing it is only half the battle, right? It has to execute the fallback plan flawlessly. If the engineers simulate a broken resistor, the computer has to instantly pivot, invoke the stator copper loss hack we talked about, and commandeer the virtual motor to safely bleed the 800 volts down to less than 60 volts in under 2 seconds. And it must do it with zero damage to any virtual hardware.
It is the ultimate final exam. The system must prove that no matter what combination of physics, weather, or component failure is thrown at it, it will always fail safely.
So what does this all mean? We've gone from sticky grease on a frozen metal relay to invisible magnetic ripples predicting the future, to hacking a motor to act as a space heater, to X-raying microscopic air bubbles in solder, and finally to physically and electrically torturing the system in a paint shaker. It completely reframes what a car actually is.
It really does. This raises an important question about the evolution of modern engineering. For a century, we built machines simply to function. A gear turns a wheel. Gas explodes in a cylinder. But with the incredible, terrifying energy density of modern electric vehicles, simply functioning is no longer sufficient.
Right.
We've been forced to build highly intelligent, deeply paranoid systems whose primary objective is to constantly monitor themselves, anticipate their own physical degradation, and above all else, fail safely. The massive complexity we've discussed isn't there to make the car go faster or drive smoother. It is exclusively there to contain the violence of the physics.
We've traced the entire incredible journey of an EV's power timing. We've seen the fundamental root causes of failure where physical and digital worlds clash. We've seen how the dual-core technical architecture stands as a brilliant defense. We explored how indestructible hardware design choices create a bulletproof blueprint, how robotic precision on the factory floor enforces those choices through strict process controls, and finally, how brutal production validation tests prove the system works.
It is a phenomenal orchestration of thousands of tiny, invisible details, all executing flawlessly every single time you want to, buy groceries.
So the next time you sit in an EV, you put your foot on the brake and casually press that start button. Just take a split second before you put it in drive. Think about the thousands of microscopic safety checks, the digital handshakes fighting through electromagnetic shockwaves, the robotic wrenches that tighten the bolts beneath you, and the thermodynamic battles happening in less time than it takes to blink. The real marvel of modern electric vehicles isn't just how fast they can launch from 0 to 60. The true miracle is the exhausting, invisible engineering required simply to go safely from off to on.